All right, so we're going to start here with part 2 of this video where we're talking about assigning chemical shifts for specific signals corresponding to these small molecules. So we're ramping up complexity in this last couple of examples in terms of things we have to think about. So let's start again looking at number and types of expected signals. So if we start up here at this methyl group on the ethoxy group, I would expect that methyl group to correspond to one independent signal, which is different from its CH2 neighbor B. Because I can't rotate around the carbon-carbon double bond, these two methyls C and D actually are chemically distinct from each other, so we would expect to see an independent signal for each of those. The hydrogen directly attached to the carbon-carbon double bond, signal E, we would expect that to be an independent signal. And then we have CHs at this carbon holding the oxygen. I would expect that to be a signal F. We have another neighboring CH directly attached to the carbon holding the nitrile, call that G. And then this methyl at the bottom, call that methyl H. Okay, so we're going to expect that number of signals. Now we need to start parsing what we would expect each one to look like. So let's work through looking at chemical shift and expected splitting first. I think a useful exercise is to look and see if you can guess which one should be farthest downfield. I think what you would hopefully pick, if you look at the table on the right here, is that signal E, this signal that's directly attached to the carbon-carbon double bond, the vinylic position, that should be the signal that's farthest downfield due to that phenomenon of diamagnetic anisotropy. So I can look at that signal. I can find really only one signal in the spectrum that fits in that range where we would expect the signal. I see a doublet. If I look at signal E, its only hydrogen neighbor sits on carbon F, so there's one neighbor. I would expect that to be a doublet, and I have a doublet, so I can assign this peak here as signal E. Now if we want to think moving to the right of the spectrum, what should be the next highest chemical shift signals? I think what you would clue in on based on the chemical shift list that we have would be the hydrogens at carbon B and the hydrogens on carbon F. Those should be the next farthest downfield because they're directly attached to an electronegative atom. So those carbons are attached to electronegative oxygen. So I would expect their chemical shifts to be the next ones that we would see. Now let's look at the splitting pattern we would expect for each one of those. B has 3 hydrogen neighbors on carbon A, so I would expect that to show up as a quartet. Typical of what we would expect for a CH2 attached to a CH3. F is a little bit more complicated. It has hydrogen E on its left and it has hydrogen G on its right. So it's got 2 neighbors, so I would expect F to arise as a triplet. And if we look down at the spectrum, we have this series of peaks that are a little bit more complicated than what we're used to looking at, right? It kind of looks like a quartet, but it also can kind of see something else buried underneath the quartet, right? What we're seeing here is that the chemical shift of B and F are so similar that they are sitting directly on top of each other. So that multiplet that we see, which is really a quartet sitting on top of a triplet, that signal corresponds to both B and F. So we can assign both of those hydrogens to that signal. If we continue to move to the right on the spectrum, the next highest chemical shift we would expect corresponds to hydrogen G, because hydrogen G is flanked by that nitrile group, which is also relatively electronegative. If we look at signal G, it has 3 neighbors at H and 1 neighbor at F. So we have 4 neighbors. We would expect this to show up as a pentet. And we do see a nice pentet here, a little bit below 3 parts per million, and that corresponds to signal G. Okay? And so at this point, we're sort of down to really only needing to pin down 3 other signals. We have methyl group A, we have methyl group C, and methyl group D. We also have methyl group H, right? So we really have 4 signals that we've got to pin down. So if we look at C and D, we know that C and D have no hydrogen neighbors, so they should be singlets. These 2 singlets that we see here in the allylic position, again, farthest downfield of the remaining signals, those 2 singlets are going to correspond to C and D independently. Now what we have left is a doublet and a triplet. We can assign the triplet to signal A because A has 2 chemical neighbors on B. And so that triplet, that corresponds to A, and then by process of elimination we have H here, and it makes sense that H is a doublet because it only has 1 chemical neighbor at G. All right, if we move on